We have been conducting hypothesis testing for claims made with respect to a population mean. We now extend this procedure to test for claims being made with respect to a population proportion. That is, we introduce hypothesis testing for a population proportion rather than a population mean. The 4-step procedure for hypothesis tests is applied with minor modifications. This is illustrated by way of an application. We will now look at hypothesis tests involving a population proportion rather than a population mean. Let us motivate it by an example. A medium-sized university in the US introduces a new lunch facility on campus on a trial basis. The university operates the lunch facility for a few months and then decides to survey the student body. Based on the survey, university would make this facility a permanent fixture or do away with it. Specifically, if more than or equal to 70% of the student body approves of it, then the facility would be made permanent, else it would shut down. The university conducts a survey with 750 randomly selected students on campus and finds that 510 of these students, or 68% of the sample students, approve of the new facility, and the remaining 240 students, or 32% students, do not approve of it. Based on the criteria set by university, should the facility be made permanent? Here, the quantity of interest is the population proportion rather than the population mean. Specifically, the university would continue with the facility if more than or equal to 70% of its entire student body approves of it. However, the university only has a sample of 750 responses from this population of student body, and it needs to make a decision based on this sample. This situation is apt for a hypothesis test. However, the hypothesis test here would be for a population proportion. The 4-step procedure remains the same with a few modifications. Step 1 is to formulate the null and alternate hypothesis. The null hypothesis here is that the population proportion, denoted by lowercase p, is greater than or equal to 0.7 or 70%. The alternate hypothesis then becomes p, the population proportion, is less than 0.7. Step 2 is to calculate the test statistic. Here we will be using the z statistic. This is one change that happens from the hypothesis test we have been running for the population mean, where we have been using the t statistic. All hypothesis tests involving a population proportion will be using the z statistic. This is calculated as p bar minus p divided by square root of p times 1 minus p divided by square root of sample size n. P bar here is the sample approval proportion obtained in the survey, which is 0.68. P is the hypothesis population proportion around which we wish to conduct the hypothesis test. To calculate the z statistic, we need a value for p bar, which is our sample proportion. In this case, it is 0.68. Then we need a value for p, the population proportion around which we wish to test the null hypothesis. In this case, it is 0.7. We need a value of n, the sample size, which in this case is 750. 750 students were surveyed on the campus. So given these values, z statistic is calculated as is equal to p bar minus p. So open parenthesis, my sample proportion minus the population proportion around which I wish to test the null hypothesis, divided by square root of p times 1 minus p by n. So, square root of p, which is a population proportion, times 1 minus p divided by square root of sample size. And notice, since we have the square root outside the big parenthesis, we simply put in the sample size there. Close parenthesis. So once again, my z statistic is p bar, which is the sample proportion, minus the population proportion around which I wish to test the null hypothesis, divided by square root of p, population proportion, times 1 minus p divided by sample size. So that is my z statistic, a negative 1.1952. One caveat in using the z statistic is that the product of sample size times the sample proportion obtained from the survey should be greater than 5. So also the product of sample size times 1 minus sample proportion should be greater than 5. Both these conditions are met in this application. Had they not been met, we could not have done this particular hypothesis test for the population proportion. Step 3 in the process is to calculate the cutoff values for the z statistic. This is a one-tailed test with rejection region on the left hand side, and also since no significance value is mentioned, that is, no value for alpha is mentioned, hence we would choose alpha or the significance level to be 0.05, which is the industry standard. The cutoff value is calculated using negative absolute value of norm dot inv alpha 0 1. So the cutoff value z cutoff is calculated as a negative of absolute value of norm dot inv. So a negative, then the absolute function a b s open parenthesis norm dot inv open parenthesis the value of alpha, the alpha in our case is 0.05 comma 0 comma 1 close parenthesis, and then to match up the parenthesis one more close parenthesis. So that will give me the value of my z cutoff, which is a negative 1.6449. As a side note, had the rejection region been on the right hand side, we would have used positive absolute value of norm dot inv alpha 0 1. But the same logic, if it had been a two-tailed test, we would have used plus minus norm dot inv alpha by 2 0 1 for the two rejection regions on the right and left. Step 4, the final step, is to check whether the z statistic falls in rejection region. Our z statistic is negative 1.1952 and the rejection region is to the left of cutoff value negative 1.6449. The z statistic does not fall in the rejection region. Hence, we do not reject the null hypothesis. The university cannot reject the claim that more than or equal to 70% of its entire student body approves of the new lunch facility. Thus, the facility should be made permanent.